Hi, I'm Thomas Wang and I am presenting our work from CMU on cloth region segmentation for robust grasp selection. This is joint work with Jianing Qian, Lucian Zhang, Brian Okorn, and David Held. Cloth manipulation is a difficult task because the deformability of fabric complicates both perception and planning. While we could try to infer the full crumpled configuration of a cloth, it is difficult to do so from a single observation. We ask whether there is a simpler representation that is easier to learn and still allows us to perform a grasp suitable for smoothing and folding. We focus on the problem of grasping a cloth on its true edges and corners. We distinguish between true edges and apparent edges like folds and wrinkles, since grasping a true edge aids downstream folding tasks. The same applies to true corners versus apparent corners. Some previous work simplify the perception task using simulation or fiducial tags. Other approaches integrate perception with interaction with the cloth, leading to perception runtimes in the tens of seconds. In contrast, our perception pipeline runs in a quarter of a second. Other papers do not explicitly reason about the grasp direction of the cloth. Our work shows that reasoning explicitly about the grasp direction, as well as directional uncertainty, leads to large improvements in grasp success rate. We first train a network that takes a depth image as input and outputs a segmentation of true corners and edges. We obtain ground truth labels by painting a cloth and collecting images of it in various poses. Color is only used during training to obtain ground truth. The network only sees depth images. The network is also trained to predict an inner edge mask, shown in green, which helps determine the direction of the cloth edge. To form the dataset, we collect 8 minutes of video, or approximately 7,000 images, in which a human manipulates the painted cloth. Example images from the dataset are shown. This training method does not require expensive human annotations for each image, as we programmatically extract ground truth labels using color. The data collection could be further automated by having our robot arm manipulate the cloth in a self-supervised manner. Our network architecture is based on UNet, which we trained from scratch. We modify the network to accept a single channel image, and we add batch normalization layers for a slight performance improvement. Additional training details such as training hyperparameters are provided in our paper. We train the network using pixel-wise binary cross-entropy loss. The network outputs key maps for k classes, with k being equal to 3 for outer edges, inner edges, and corners. The loss against the ground truth is summed across the 3 classes. To compensate for the imbalance of positive versus negative pixel labels, we weight the loss accordingly. The output of the segmentation network provides per pixel classification of outer edges, inner edges, and corners. We now aim to choose a grasp point and direction given this output. We zoom into a crop of the output to better illustrate the method. We demonstrate the grasp selection method for selecting a grasp on a cloth edge, and the process is the same for corners. We define the set of outer edge pixels to be EO, and the set of inner edge pixels to be EI. For each outer edge pixel P in EO, we find the corresponding inner edge pixel Q in EI with the smallest L2 distance. The sparse set of these outer to inner edge pixel correspondences are visualized in the image as pink arrows. This outer to inner edge correspondence provides each pixel with an estimate of the cloth edge orientation. The direction also serves as the approach direction for a grasp centered on the outer edge pixel. From this dense set of correspondences, we will choose one as the best grasp point and direction. To determine the best grasp point, we introduce the concept of direction uncertainty and use this concept to choose the grasp with minimal uncertainty. First, we define 2 values, f cosine of p and f sine of p, as the cosine and sine of the angle formed by the direction vector of p with another direction vector q. We can compute these f cosine and f sine values for every outer edge pixel in a local neighborhood of p. nk represents the local neighborhood of the k outer edge pixels around p. x0 and x1 are therefore sets containing the angle difference of how much the direction vectors near P deviate from the vector associated with P. As can be seen in the image, there are some regions where every direction vector in a neighborhood points in a similar direction, and some regions where nearby vectors point in different directions. We compute the covariance matrix of the angle components in x0 and x1, and we do this for every outer edge pixel P in the image. The sum of the diagonal of the covariance matrix correlates well with the total variance in the edge direction angles. We find the outer edge pixel and direction vector with lowest directional uncertainty and select that as our grasp point and direction. The new figure shows how our method marks areas where multiple inner edges are present as areas of high uncertainty, whereas areas with a single inner-outer edge are shown to have low uncertainty. To summarize our grasp selection method, for every outer edge pixel, we find the vector to the nearest inner edge pixel. This vector represents a guess of the cloth edge direction at that outer edge pixel. We compute the uncertainty associated with each vector by comparing it with its neighbors. Then we choose the grasp point and associated direction with the lowest directional uncertainty. In order to execute the grasp, we define a non-learned sliding grasp maneuver. The sliding maneuver gives the robot a better chance to grasp the edge of the cloth lying flat compared to a pinch grasp, and helps isolate an edge or corner lying on top of the rest of the cloth. We evaluated our method on grasping isolated edges and corners of the cloth. For each grasp attempt, the cloth was dropped from a height of 0.1 meters to form a random cloth configuration. The system attempted an edge or corner grasp, and then the grasp is evaluated. The grasp was considered successful if there were no folds or a single small fold. We fixed the threshold on the length of a single fold that would be considered a failure before running the experiments. The single fold displayed here was considered a failure as it exceeded the threshold. Grasps with multiple folds were always considered failures. Please refer to the paper for further details on the experimental protocol. Here you can see an example of our complete system. Our method observes a depth image of the crumpled cloth and segments it. It then estimates the grasp direction and directional uncertainty. Finally, we grasp a corner point with low directional uncertainty. As you can see, we are able to grasp the cloth corners or edges from many crumpled configurations. We evaluate against image processing baselines for edge and corner finding and show that our method outperforms them in both edge and corner grasping success rate. Here we show an ablation experiment demonstrating large drops in performance if we remove our methods for estimating grasp direction and selecting a grasp point, showing that both elements are key contributions of our approach. No direction prediction uses the cloth segmentation network, but determines the grasp direction by fitting a bounding box around the segmented outer edge pixels and setting the grasp direction to be the vector pointing to the center of the box. A random grasp point is selected from the set of outer edge pixels. No directional uncertainty uses this cloth segmentation network and our method for determining the grasp direction. However, this ablation still chooses a grasp point randomly. As can be seen, the direction prediction as well as the directional uncertainty are both crucial components for our method for a high grasp success rate. We noted two main causes of failure in our experiments. Failures occurred due to segmentation error. Because the cloth was very thin and the input depth images are noisy, the network may predict that the edge bleeds over onto the surface of the table. In this case, the misdetection causes the grasp point to be too low to catch the edge of the cloth. Failures also occurred when the cloth predicted a valid grasp but failed to account for problematic nearby cloth configurations. In this case, The gripper picks up multiple folds of the cloth because it does not account for the folds it would intercept during the sliding motion. Note that some segmentation error for some images has also occurred in this particular case. Here are some video examples of the failure cases. We demonstrate the robustness of our method to variations in color and cloth size by grasping other cloths. Because our network uses depth as input, it can be used on colorful and patterned fabrics. Since the network is fully convolutional, it can segment the edges and corners of cloths of different sizes. The robot was able to segment and grasp the corners and edges of cloth not seen during training. Here you can see some examples of our method grasping cloths of different sizes and textures. In summary, our method segments the true edges and corners of a cloth. It selects a grasp taking grasp direction and directional uncertainty into account. It grasps cloth corners and edges from many complex crumpled configurations. We demonstrate that our method is robust to variations in cloth size and color. We'd like to thank our sponsors for funding this research. Thank you for watching, and please see our paper for full details.